so welcome everybody. Today we're going to be discussing drawing FBDs and Newton's first laws. FBD stands for force body diagrams or free body diagrams. Okay, so with free body diagrams or force body diagrams, we are essentially talking about forces, as the name gives it away. With force, you have to remember that it's a vector. They're going to have arrows, and those arrows are going to be relative with size and so on. And those arrows indicate direction. So again, vectors, you have direction and magnitude. Remember that magnitude is simply a fancy term for numerical value and units. All right, so with free body diagrams, they're used to show relative magnitude, again, numerical value and the direction of all forces acting on the object in a given situation. The free body diagram is going to be vector diagrams, and you are going to have to draw many different arrows in order to depict what's happening at a given moment. The key point being a specific time in the situation as opposed to long term, and we'll go ahead and discuss that more in detail. Okay, the size of the arrow is reflective on the magnitude of the force, and the direction also reveals the direction in which the force acts. So again, if you're pushing, from left to right, the arrow is going to be on the right-hand side. It's in the direction in which the force acts. We'll see many of these examples. It'll make more sense. But you just have to make sure that just like any other vector, they are relative and they are reflective of the magnitude to each other. So if you have a value of 3 on the right-hand side, whatever size that arrow of the 3 is, it should be the same size on the left side if it's also a 3. Or if your value on the left side is a 5, it shouldn't be smaller than the 3. So you have to put relative to each other and reflective of the magnitude of the force. Okay, so what free body diagrams look like in a nutshell is something like this. Now this has multiple different forces in it, and we'll discuss how many could have or how many should have, but these are some of the more common examples of forces that you'll see. Every free body diagram that you draw should be drawn with a box, and that's so that you can put the mass inside of it. So again, it's called a free body diagram or a force body diagram. All of the vectors and your arrows are on the outside. So all the forces go on the outside and they all point outwards. None of them point inwards. But the mass should always be put inside if you happen to know the mass of the object. So you're just going to draw a square. We don't care what the object is. Everything for us is going to be a square. Now with the red line, you see that I've drawn it in there and put it as a surface. So essentially what happens is when you have a surface, you have F normal or Fn at the very top. F normal is weight. So remember in previous classes, we've discussed that weight and force are not, or I'm sorry, weight and mass are not the same thing. Weight is a force and mass is not one. So the equation is F equals ma. If weight is the F, it can be the same thing as equal to m and a, meaning it can be both mass and acceleration. So remember that weight is a force and mass is not. Mass will not change. So regardless of where you go, mass will stay the same, whereas force and weight depends on gravity, so weight will change. All right, on the left-hand side, we have force friction. On the right-hand side, we have force applied. Top, we've got force normal, or Fn. And again, that's only available when you have a surface and the object is touching the surface. So if it's not touching a surface, you will not have F normal. F gravity is always there. Now, the key thing for F normal to remember is that it is always perpendicular to the surface, not the object, perpendicular to the surface. Whereas F gravity is always straight down from the object. You'll see depictions of this later, but just a heads up. All right, like I said earlier, basically free body diagrams or force body diagrams, it's customary to use a box or a small circle. I personally suggest to use a box for everything, and you draw the force arrow from the outward direction. I know it says here from the center, but we're going to use the center of the box to give us room to write the mass number. So just draw it from the outside, always going outwards. Nothing goes inwards. And it's essentially in which the way the force or the direction is acting. So when it says in one example of free body diagram is shown to the right, it was essentially this picture right here. All right, so that free body diagram depicted 4 forces acting on the object. There is essentially, objects don't always have to have 4 forces acting on them. That number could change. The minimum is always 1. The maximum could vary. So you could have 1, 2, or 3, or even more. There's really no hard fast rule about how many there should be, other than the fact that there's always one, which is Fg, or force gravity. That's always present in any problem. The other only rule for FBDs is that you got to depict all the forces which exist in that given situation. And let's just think about this hypothetically, and this is sometimes a quiz question or a test question. Let's just say a punter punts a ball, and when the ball's in the air, what forces are acting on it? Well, most people will think about the fact that, well, the punter had to kick it, so there was a force there, and then it's in the air. But the problem is saying, when the ball is in the air, what forces are acting on it? So you can't say that the kicker is still kicking it, because his foot is not attached to the ball anymore, is making contact with the ball. So that's what I mean by in that given situation, is if the ball's in the air, you can't depict the force that caused it to get into the air, because that was way a couple seconds ago prior. So essentially what you're doing is depicting in that given moment when the ball's in the air. And when anything's in the air, of course, you're always going to have Fg, or gravity, force of gravity applying to it. All right, so when you're going to do FBDs, it's important to know the different types of forces. And like I said earlier, it's a description of the physical situation as of what's happening during that scenario. We're like with the punter kicking it and the ball being in the air. So you got to pay attention to what the question is asking. Likewise, you have to identify which forces are present and then determine the direction in which each force is acting. So you kind of have to think through it a little bit, but it helps out to draw these, and you're supposed to draw them because it'll help you solve these problems as we get into forces for the next couple of weeks. Always remember to label the force and have them relative to each other. And when I say relative, I mean X is its own separate thing and Y is its own separate thing. So the size of the arrows on the X should be relative to each other, but the size of arrows of X and Y aren't necessarily for each other. So keep those separate, but make sure that they are relative to each other as far as X is concerned, with the other X side, whether it's horizontal left and right, and the Y side with up and down. All right, so let's go ahead and look at our first example. A book is at rest on a tabletop. Diagram the forces acting on the book. Okay, so when you see this problem, first you got to ask yourself, is it making contact with something? The answer to that is yes. It's on a surface, the tabletop. So we know we're going to have to depict the surface. The other key thing is the book is at rest, meaning it's not moving horizontally or vertically. So we're also going to have to depict that as well. So imagine a book at rest, or think about your laptop right now, your Chromebook, whatever you have, and it's on the tabletop. That's what we're going to be depicting in the next diagram. So you should draw the surface, making contact with the object. Again, you should always have squares. In this worksheet, they just drew circles, but drawing a square will help out if we knew the mass. So when you draw your square, it's going to be making contact with a flat line. That flat line is your surface. Again, whenever you have a surface, F normal is present. So F normal is going upwards, and FG is always downwards. As a reminder, like I said, F normal is always drawn perpendicular to the surface, not the object, but perpendicular to the surface, whereas FG is always straightly drawn from the object downwards. Okay, so Fn is equal to Fg. In this case, force gravity is pulling it down. However, the surface is making contact with the book, and essentially it is resisting for it to go down further. It's also the same concept of you sitting on a chair. It could be the same exact scenario. You're making contact with the chair. You have the surface as a chair, and your weight, your F normal, is pushing upwards, and your FG is pulling you down, and you're not moving anywhere. So Fn is equal to Fg, and we'll get into calculations of finding weight and so on in a different time. Okay, so now we see the whole picture all together. Force normal, or Fn, is weight. Weight is different from mass, so just keep that. This is an important thing. I've said it multiple times, and I'm going to go ahead and continue to say it. Weight and mass are two different things. So remember, one of the easiest ways is if someone complains about wanting to lose weight but not having to do anything, such as going to the gym or changing their diet and habits, the easiest way for them to lose weight is to go to a different planet, to go to the moon or something like that. The gravity on the moon is 1.6 compared to 9.8 on Earth. So when you take your weight in the moon, it's a lot lighter than it is on Earth. So the easiest way for someone to lose weight is to simply go to the moon. Now, the cheesy way that I've taught you guys is to remember the infomercials, for example, for anything, and they always say, but wait, there's more. Of course, they're talking about as WAIT, waiting, but we're going to go ahead and treat it as weight, as in what we're referencing right now. So just remember, but wait, there is more, meaning that if there can be more weight, there can be less weight. And if you can have more or less of something, it means it fluctuates. Nobody says, but mass, there is more. So it's but weight, there's more. And again, Fn only exists when a surface is present. So we draw the vector arrows. You'll see that both of them are the same size. And as a result, we can say that Fn is equal to Fg. And as a result of this, the object is not moving vertically at all. We don't have any arrows horizontally because there's no mentions of anything pushing it or stopping it, horizontal movement. So again, we're just depicting as of what's happening in that given situation. All right, moving on to example number 2. A ball is suspended, motionless from a ceiling by a rope. Diagram the forces acting on the ball as it rolls onto the rope. So let's go ahead and this is a disco ball being discussed. And what we've got is essentially now that object, the disco ball, is not making contact with any surface. So we no longer have a straight line underneath it. Fg is always present, going down straight from the object. The force for a rope, a string, or a sling, such as the stuff for your backpacks, purses, whatever, are indicated by force tension. So think about the word tense, and if someone's tense, they're tight. So if you can use something to tighten up, such as a string, sling, rope, whatever, then that's force tension. And in this case, it's the disco ball is suspended motionless from the ceiling by a rope. So force tension is going upwards, and again, everything's outward, and force gravity is pulling it down. The arrows are again equal to each other, that neither one is bigger than the other. If we had Fg drawn as coming further down, that would have meant that Fg is winning and that the disco ball was actually falling somehow. But that's not the case. So it's suspended in the air. F tension is holding it up with the one single rope. Now, as you look at the top, I've added in the fact that each rope or string or sling or whatever you're using requires its own separate vector force. If this disco ball was being held by 2 ropes, we would have drawn 2 F tensions. But those F tension vectors would have been half the size of the current one. So let's just say hypothetically, the value of the F tension is 10. And the Fg right now is also negative 10 because it's downwards and it's a negative. So Fg is a negative 10 hypothetically, and F tension is 10. And that's one single rope. If we had 2 ropes, the F tension vector arrow would have been cut in half, and you would have had 2 of them. And each one of those would have been a value of 5. 2 5s add up to a 10. If it was being held by 3 ropes, the original F tension vector that you see would have been cut down into 3 equal size of smaller size, and each one would have been about 3.33 or so to add up to 10. So just keep that in mind when you start separating them and how many vectors you have. Okay, an egg is free falling from a nest in a tree. Neglect air resistance, diagram the forces acting on the egg as it falls. So one of the key words is always to pay attention to is free falling, and we'll get into that in a second. So free fall means that the only force acting on an object is gravity. We did this with free fall objects previously, we just never drew FBDs for them. But we said when something's free falling, you no longer have control over it. Nobody does. The only thing that's causing it to fall down is gravity. So we're neglecting air resistance. So we have an object and there is F gravity, always pointed straight downwards from the object. And that's it. That's the easiest FBD you're ever going to draw. But the key thing to it is to always pay attention to the key words, free falling and neglecting air resistance. Now, for most problems, we are always going to be neglecting air resistance unless they specifically tell you that there is air resistance involved. And we'll have an example of that too. But there's differences between the words free falling and simply falling. So just keep that in mind. All right, moving on to problem number 4. An egg is falling. Now, that's the difference right there. It's not freely, so we're not neglecting air resistance. So if it is free falling, it's only gravity, and we are neglecting air resistance. If it's simply falling, then it's we're not neglecting air resistance. So an egg is falling from a tree, from a nest in a tree. Diagram the forces acting on the egg as it falls. Well, we already know that it's going to have Fg no matter what. So it's going to look similar to the previous one, but the difference is Fg is going to be pointed down, and F air resistance is going to be a smaller arrow than Fg. You can't draw the same size because if you drew the same size, it would mean that it was at constant velocity. It could be falling down, but it just wouldn't be accelerating. And that would be considered terminal velocity. But F air resistance is actually less value than F gravity, which means the vertical side, the F gravity is winning, if you want to think about which side is winning and which side is moving in that direction. So F gravity has a larger arrow and it's greater than air resistance, so the object is moving and accelerating downwards. So make sure that the arrows and vectors are relative to each other, and if you're going to depict this, the F air resistance has to be smaller than F gravity. All right, number 5. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider frictional forces, neglect air resistance, diagram the forces acting on the object. So there's a couple of things to pay attention to, and there's a couple of key words. It's a rightward force and a rightward acceleration. Anytime you have anytime you have an acceleration, doesn't matter which direction it is, that direction has to have a larger vector, larger arrow size than the opposite side. So if we go back one slide, we can see that we were having a downward acceleration. So the arrow that was pointing down for F gravity was larger and bigger than the arrow that was for F air resistance. So now we have a rightward acceleration, which means to the right side, this vector is going to have to be longer than the arrow on the left side. And the other thing is that it's moving across a desk, meaning that it's on a surface and it's making contact. So there's a couple of things to worry about. Also frictional forces, which we're going to get into as well. The thing with friction is it always goes in the opposite side of direction. So with friction, if you're moving to the right, frictional force is to the left. If you're moving to the left, friction force is to the right. It's always in the opposite direction of motion. So we know we're going to the right, the force is applied to the right, so our vector for the force being applied is going to be to the right side. Our vector for frictional force is going to be to the left side, and we're going to go ahead and depict those. But first things first is let's just get the basic out of the way. You have your square or you have your circle, you have your surface, and we are going to depict the two things that are going to be there. F gravity, which is always present, and because there's a surface there, we have F normal. This object, which I believe was a book, is not moving vertically. So those two are essentially the same size. Now that you've gotten this out of the way, we're going to go ahead and worry about the direction and the vector size on the right, and as well as to the left. So like I discussed earlier, we have a right arrow that's going to be larger to the right compared to the left. This is because the object is accelerating rightward. So the right side has to be quote unquote winning. Think of it as a tug of war. So the right side is winning. And the arrow on the right is much larger than the arrow on the left. So F applied is anything that's a push or a pull. So push or pull forces are considered as F applied. And force friction, like I said, is always in the opposite direction of motion. So if the object is moving to the right, friction is to the left. If the object is moving to the left, friction is to the right. For most of our problems, even if they don't include the direction, you're going to assume motion is to the right and friction is to the left, unless they specifically state otherwise. The reason for that is because you want friction to be negative because it counts against you. So with forces, just like anything else, it is a vector, like I mentioned earlier. And when you have vectors, you're going to have negative values. So Fg is a negative value. F friction is a negative value purely because it's on the left-hand side and on the right-hand side. If F friction was on the right-hand side, then yes, it would be positive. So again, think about directions. Up and right are positive, left and down are negative. All right, so back into this problem, we have Fn is equal to Fg, which is why the object is not moving vertically. It's at rest from a vertical standpoint. The force applied is greater than force friction, which is what is causing the rightward acceleration. And force of friction, as I mentioned earlier, is always in the opposite direction of motion. So these are some key things to be aware of. Again, if I'm saying it multiple times, it is because these are the type of questions that you're going to come across in quizzes, tests, and so on. All right, so we're going to be moving forward. I know some of you may be just writing some of these down, but the next problem is going to say that a rightward force is applied to a book in order to move it across a desk at constant velocity. So the reason I'm reading that problem right now for number 6 and keep it on 5 is so that you can compare the words to number 5. So number 6 is going to say a rightward force is applied to a book in order to move it across a desk at constant velocity. That's a big difference as opposed to rightward acceleration in number 5 compared to constant velocity in number 6. Consider frictional forces, neglect air resistance, diagram the forces acting on the book. So pretty much 95% of it is the same exact problem, same exact scenario. The only difference is in number 5, we had a rightward acceleration, and in number 6, we have constant velocity. So let's go ahead and see how that depicts a change and how your FBD should be drawn as a result of it. So there's number 6. Again, it's still moving, but at constant velocity. So remember that the arrows and the vectors don't indicate movement, they indicate acceleration. The movement happens when you have an arrow that's larger in one side compared to the other. So same exact scenario, book is at rest vertically, it is moving horizontally, but when you draw it, you have FG, you have the surface, FG and F normal are the same size. And now we have two arrows that we're drawing, and these two are equal to each other. So F applied was the force of the push, and force friction is in the opposite direction of movement. So like I said earlier, they didn't mention which direction it was moving, and if they don't mention it, always assume that motion is to the right, so that motion is positive for you, and that friction is negative because it's to the left. So while they didn't say which direction it was, we're going to assume that it was to the right. The object is moving to the right, but it happens to be moving at constant velocity. And when it's constant velocity, the arrows or the force vectors are the same exact value, just opposite of each other. So let's go back to hypothetical numbers. We can say that Fg is supposedly negative 10, or let's just say negative 100, because it purely depends on mass. Do not think that Fg is negative 9.8. I was just using negative 10 to make it easy on the math. So Fg is not negative 9.8 at all, unless there's one specific scenario. So if you're ever asked to calculate Fg, there's a way to do it. Don't assume it's negative 9.8. Force of gravity is not the same as acceleration due to gravity. Excuse me. Those are two different things. So if Fg is negative 100 newtons, F normal is the same size, which is 100 newtons. Now, those two are relative to each other. The magnitudes we drew them as each other. Now, let's just say that force applied only happens to be 30 newtons. Again, it's the arrows on the right and left don't have to match the sizes of the top and bottom one. So keep that in mind. Although if we want it to be, we should technically do that, but you don't have to. So force applied, let's just say, is 30 newtons. That would make force friction a negative 30 newtons. So they balance each other out. There's still movement. It just happens to be no acceleration. So constant velocity means no acceleration. And think about motion graphs. Think about motion problems that we did. If an object, let's just say you're driving in a car and you put it on cruise control at 60 miles per hour, you're going to continue to drive at 60 miles per hour. But you've basically put it on cruise control, which means do not accelerate more and do not accelerate less. Don't change the speed at all. So you're going to go at 60 miles per hour for the duration that cruise control is on. It doesn't mean you're stopped in place. You're still continuing to move. It's just that you have no acceleration. And when you have no acceleration, it never changes from that 60 miles per hour. Likewise, this object here, it's moving to the right, but it's not accelerating to the right. So keep that in mind. All right, so constant velocity, like we've said, it means no acceleration, and no acceleration, of course, means zero acceleration. Fn is equal to Fg, and F applied is equal to F friction. So whatever value we give to the right, if we knew whatever force applied was, it would be the same exact value on the left with a negative value. And if we said Fg is a negative 100, F normal is 100. And speaking of F normal, I mean, it should go on saying F normal is your weight, and the only way you can ever depict a weight on something is if it's on a surface, on a scale, or anything like that. So again, F normal, because it's an upward force, will always be positive. So there is an equation in your formula sheet that says to find weight, and it actually uses Fg. And you're supposed to go ahead and use mass times acceleration due to gravity, which is negative 9.8 times the mass, and you get a negative number because you're solving for Fg. But weight is always positive because it's going upwards. So just keep that in mind. Nobody has negative weight. Okay, number 7. A car is stopped at a light. So it's a little bit different problem than the book, but it's actually drawn the same exact way. The book being at rest. The car is, again, making contact with the surface, the road. So you have Fg present at all times, no matter what. And in this case, you have F normal. There is no forces causing it to go right or left. The car is stopped, so we're not going to depict arrows to the right or left. We're only depicting the exact moment, that exact situation. So in this scenario, F normal is equal to Fg. Okay, I mentioned this earlier. Fn is always drawn perpendicular to the surface, and the symbol for perpendicular is to the left of it, not to the object or to Fg. So we've seen a bunch of problems, and it just looks like F normal is always going up, straight up, but that's because every surface that we've had has been horizontally straight. So just keep that in mind, that Fn is always drawn perpendicular to the surface, not to the object, and not to Fg. Fg, on the other hand, is always drawn straight down from the object. So it doesn't matter how the angle looks of the surface. It's purely on the object, and it's always straight down from the object. All right, number 8. A skydiver is descending with constant velocity. Consider air resistance, diagram the forces. So descending means that it's obviously moving downwards. However, you have constant velocity. So again, these are the keywords you're going to have to pay attention to. Constant velocity means no acceleration. So when we draw our skydiver, it's going to be a box. There is no surface because they're descending, they're in the air, but there's always Fg, and we're going to go ahead and consider air resistance. So now we have essentially that depiction of it is Fg goes down, F air resistance is going up, and Fg is equal to F air resistance. And that's the only way in which you're going to obtain constant velocity, and which means no more acceleration. So this would be essentially what a skydiver um, experiences as terminal velocity, meaning you can't go any faster. So it can no longer accelerate to go down faster, but it is still descending and moving down. So if you go back a few slides, and if you look at your notes, our first F air resistance problem was actually problem number 4, and that was the one that said an egg is falling, not freely, don't neglect air resistance. In that case, it was falling. They didn't mention constant velocity, so we assumed that it was accelerating downwards. So for that problem, Fg was greater than F air resistance. For this problem, they specifically told us that it's at constant velocity, which means the two forces need to be balanced or equal to each other. All right, number 9. So this is our first scenario in which our surface is different. So a car is parked on a sloped street. Again, F normal is drawn perpendicular to the surface, not the object. So that's why F normal looks to be at that angle, because it's to the surface. Fg, however, is straight down from the objects. So that's why you see it looking a little bit differently. Now, we also have force friction, and this is something we're going to get into at a different time when we teach friction, but the car is not moving. There is 2 different types of frictions. There's static friction and kinetic friction. Static is meaning that it's the amount of friction needed to require to keep something stopped from moving, and then kinetic friction is the amount of friction that it needs to overcome in order to start moving. So there's different types of force frictions involved. In this case, the force friction is preventing this car from moving. In the event that for whatever reason, if there was too much force involved, or if just the car was way too heavy, and if all it took was just a slight little movement to overcome that force friction, the static force friction, it would roll down. But right now, it is not. And the reason it's depicted upwards is because, or to the right, essentially from this picture, is because if you're on a slope like that, on a street like that, the car naturally wants to go back, naturally wants to go down. So the motion of the car would have been going down, but force friction is in the opposite direction of motion. So while it looks like right now we have motion to the right, again, this is why I drew it to the red, is to emphasize that we're talking about static friction, and static friction is the amount that is required to keep something stationary. If it was kinetic friction, that's the amount required to move it. So right now it's not moving, that's the amount of static friction. All right, finally, F number 10, we're looking at a hot air balloon is accelerating upward. So again, keyword accelerating and in the direction. We always know that there is Fg involved. It's not making contact with anything because it's in the air, so there's no surface. So it just means that the up arrow or the up vector needs to be longer than the Fg, whatever that may be. To make it simplified, I just went and said that it's F applied. I understand that F applied is only for force, push, and pull. Now, obviously, this is a hot air balloon, and you could go into F thrust or anything like that. To make it simplified, we're just going to go with F applied. The concept here is to just be aware that the direction of going up is accelerating, and therefore the vector that's upwards for force applied is greater than the downward force gravity vector. So that's what FBDs are going to come down to, is you guys reading the problems, paying attention to keywords, which way is it moving, is it accelerating, or is it at constant velocity? There's a couple of keywords to pay attention to, but if you do them correctly, then everything else will start making sense. Okay. So a car, excuse me. A car is coasting to the right and slowing down. Diagram the forces acting upon the car. So kind of a key problem here, and as you can see, I've put in that it's in that exact moment. Most of you want to think about the whole picture, which is, well, if you were moving previously, you had to apply gas and so on. But the car is coasting to the right, meaning that the driver is no longer applying throttle, and they're no longer applying the gas. And the car is slowing down. Diagram the forces acting upon the car. So again, that exact moment, not the whole scenario. So let's look at how this looks. Cars on the surface, we have our surface there. We have FG and F normals present. There's no mention of a sloped street, so it's on horizontal surface, horizontal road. But we have no force to the right because the driver's not applying any kind of throttle or force to cause it to go forward. The car is still moving. All right, so this is what's known as engine braking. So the driver is no longer applying throttle. They were previously, but they're not doing it at this exact moment. So let's just say that you were going 60 miles per hour and you take your foot off the gas pedal. And at that point, you no longer are traveling at 60 miles per hour, but you also don't come to a sudden stop either because you're not applying the brakes. This is known as car coasting. So the car is coasting. It's still moving in one direction, the direction that it was originally moving. However, it's making contact with the road and there's force friction involved. Force friction is the opposite direction of motion, which is to the left-hand side. And the friction is eventually causing it to slow down. And remember, these vectors don't depict movement, they depict acceleration. And technically, the car is accelerating to the left because that's how it's slowing down. So if you go back to our acceleration lesson plans, you remember that, acceleration can be in the opposite direction of motion. And again, the simplest way to think about that is when you throw an object in the air, motion is upwards, acceleration is always downwards. So just because the car is moving to the right doesn't mean you necessarily have to draw a force vector for it, because the force diagram means to depict the forces that are happening at that moment. And this problem read, a car is coasting to the right and slowing down. Diagram the force acting upon the car. Okay, so here's my basic explanation. This is, although the car is moving to the right, there is no force applied. Technically, you could call this as F thrust, because the F thrust is for engine combustion and so on. So there's no gas, no throttle being applied by the driver. It's coasting, so no arrows are drawn. And force of friction is always in the opposite direction of motion. So had the problem said a car is coasting, didn't mention a direction, you still would assume to the right. So if the directions that were mentioned, assume to the right, make life easy on yourself so that motion is to the right, those values would be positive, and friction as a result would be negative, because you want friction to always count against it when we start doing mathematical problems. All right, so some basic, simple FBD tips. Draw boxes for any object. I know in this worksheet there was a bunch of circles and it was filled in because your two options are either basically a black circle filled in or a box. It's better to draw the box because once we get into Newton's second law and you have to do calculations, you want to go ahead and put the mass inside the object or inside the box. Force vectors, the arrows always go on the outside of the box. They also point in the outwards direction, meaning away from the box. So nothing goes in towards the box. If you see a test problem or a test question that has arrows pointing in, obviously those are the wrong answers. Now, mass, the numerical value of it, goes inside the box. The mass doesn't change, so keep that in mind. Mass goes inside the force body diagram. The FBD vectors are always on the outside. So that should be a hint for you to not mistake mass for weight. Weight is newtons, the unit for it, when we're talking physics, and mass's unit is always going to be in kg. In the event that you see a problem with mass saying anything other than kg, you're going to have to convert it. So always be aware of conversions. Sometimes you may have to go from grams to kilograms. Sometimes you may have to convert from something different, but mass always needs to be in kg and your weight is in newtons. So remember that weight is a force. It's essentially Fn, and the units are newtons. Weight changes, but mass remains the same. So weight is your force normal, or Fn, and remember that Fn is only available when you are making contact with the surface. And of course, the cheesy line, but wait, there's more. So if you can remember that, that should help you remember that if you can have more weight or you can have less weight, then weight changes, but mass does not. So keep that in mind. Okay, so this concludes our FBD portion. And now we're going to go ahead and move on to Newton's first law. Now, you've seen this before, you've taken notes over this on your own. However, I'm going to go ahead and expand a little bit more so that it is you guys understand it in more depth. So wherever you've taken notes for Newton's first law, you can start adding these to it. You may have most of this, or you can just start on a brand new sheet. Now, force is a push or a pull, and it's exerted on an object having magnitude and direction. So again, forces are vectors. You're going to have the magnitude, which is a numerical value, and you are going to have a direction because it's a vector. So the units for a force are in newtons, or in capital N. All right, the type of contact forces. And we have two different essential forces. We have contact and we have long range forces. So our first one is force friction. We've talked in that in a little bit of detail. We're going to have a whole lesson over this at a later time, but just know that friction is in the opposite direction of motion. You have force tension, which is for anything regarding strings and so on. So strings, ropes, chains, slings of a backpack or a purse or whatever you may have. And just remember that each one of those, if you have 2 ropes, you need to have 2 force tensions. If you have 5 chains, you need to have 5 force tension vectors. And then you have normal force, or Fn. That's only present when you have a surface. That's your weight. You have thrust for engines, mainly jet engine and combustion, but you can use whatever. And it's FTH. We don't deal with spring in on-level physics, so you don't have to worry about that. And then finally, force applied, which is for anything push or pull. Most of your forces will fall under force applied, unless, of course, it's the main ones on top of it. We also have gravitational weight, long-range forces, which are electromagnetic, magnetic force, and gravitational weight force. We'll get into those at a different time in this in on-level physics. So we'll do that at a later point. All right, some miscellaneous ones. F drag is the same thing as air resistance. If you just write F air, no one's gonna, do anything over it. So whatever makes sense for you. F drag or F air resistance, they're the same thing. And then F buoyancy is when you have something in water. All right, so force tension. All ropes, strings, and slings and chains use tension force. So remember that basically you can think about the word tense. If someone is tense, they're very tight. And if you can tighten something with something, then that's usually basically force tension. So rope, string, sling, chain, whatever you can use to tighten something with, it is going to be called force tension. Normal force, Fn, is your weight. It's always perpendicular to any surface that you are dealing with. An object must be touching a surface to have the normal force. So basic overview, remember that the only way you're going to read an object's weight is if it's on a balance or a scale. And the only way that's going to work is if it's making contact with that surface of a scale or balance. So normal force, the weight is always perpendicular to the surface and touching the surface. It must touch the surface to be there. Frictional force is always opposite in the direction of motion. So if you're going to the right, friction's to the left. If you're going to the left, friction's to the right. If you have a car, some of those toy cars that can go ahead and up and down on a wall vertically, you won't see this in physics problems, but just in case, if something is going down and it's making contact with the vertical surface, then it would theoretically force friction would be up. But on level physics, you're not going to deal with that scenario. Most of your frictions are always to the left or right. That's about it. Okay, so again, a bunch of stars, a bunch of highlights. In a typical year, I use so much highlighter that this class would be your highlight of your day, but this is not a typical year, so you don't see me using highlighters as much. So yeah, weight is a force. The equation is also known as equation 9. So in your formula sheet, now we've gone to additional equations. Up to this point, we were doing 1 through 6, And now we've gone into new ones, which is 7, 8, and 9. And we'll start using those. So if you want to find weight, that's equation number 9. And it still falls under the same thing. W equals mg, or it actually says F is equal to mg, and essentially F is equal to ma. So these are all roughly the same thing, but the g is basically mentioning that it's acceleration due to gravity. So even though we see F equals ma in the vertical motion, that a is a due to g. We'll see plenty of those examples. So weight does not equal mass. Remember the cheesy method, but weight, there's more, means weight can change. If we can have more of something, you can have less of it, it changes. Mass does not. Okay, Newton's first law, the law of inertia, is the tendency of an object to resist change in motion. So, something at rest is going to stay at rest and so on. And we've discussed this previously as of depending on the mass of an object. So the amount of stuff an object has is considered the mass. Mass is the same everywhere in the universe. For the 100th time again, mass does not change. And mass is basically equal to your inertia. The more mass an object has, the more inertia it has. So resistance to change. So think about a bowling ball, and if you were to go ahead and try to change its direction from rest with simply a broom, compare that to a tennis ball or a ping pong ball. If we take into consideration the mass of a bowling ball, it's going to require a lot more force than the tennis ball or the ping pong ball to change its direction than simply with a broom compared to the lighter objects. All right, every object in a state of uniform motion, constant motion, tends to remain in that state of motion unless an external force is applied to it. So this is kind of like the first asterisk, when you think about things, unless there's an external force that is applied to it. So in common sense, or common words, it's basically an object at rest stays at rest or remains at rest, and an object in motion stays or remains in motion. That's going to be held true unless you have an outside active force that is unbalanced. So if you think about if there was a situation where there is no force friction, think about a bowling lane, an unlimited bowling lane that goes X amount of distance that you never comes to an end. If you roll a bowling ball and there's no friction involved, that should theoretically continue to go straight forever. It's not going to go ahead and lose due to friction. The moment that it comes to an external force is if it starts to experience friction or if something else causes it to change direction. Imagine if somebody's just basically standing there and changes direction with a broom or a stick or something like that. All right, so the symbol that you see right there is epsilon. The Greek letter for epsilon means the sum or the net force. And an object that is not accelerating is said to be in balance. This is important to make sure you write it down. You're going to see the word balance quite often, and we're going to refer to it. Forces are balanced, net force is balanced, and so on. That means that the force or net force when forces are balanced are 0 newtons. And if you have a net force of 0, then at that point, the object is not accelerating. Doesn't mean the object is not moving. It just means the object is not accelerating, kind of like your car in a cruise control. So, again, you can be moving at 60 miles per hour on cruise control. You're moving, you're just not accelerating, meaning your speed is not changing one way or the other. And why don't objects on Earth keep just moving forever? Well, because we have friction, and that's essentially our external outside unbalanced force. Something makes contact with the surface, and eventually there's going to be friction involved. All right, so now that you know FBDs, these are some of the things some basic examples that is kind of like a review, but now we have a person sitting on a chair. We have our surface, we have our box, Fg is equal to Fn, and a net force is considered to be 0 newtons. And in that case, we can say the forces are balanced. When you're balanced, you're not moving, or you could be moving, but you're not accelerating. So in this case, it's neither moving nor accelerating, but forces depict acceleration, not movement. It's the acceleration that depicts movement. Okay, so now the key word, car moving at constant velocity. So remember that when you see these terminology, just be aware of basic stuff. Constant velocity means you're not changing your velocity, which you're not changing your speed or direction, and as a result, there is no acceleration. So when we draw this scenario, it's cars making contact, Fg and Fn are there, they're equal to each other, and then F thrust is the same as force friction. So our two vectors on the horizontal side are balanced with each other. So our net force in the x direction is balanced, meaning there's 0 newtons. And our net force in the y direction is also balanced. So just like in previous problems that we've done, whether it's projectiles launched at an angle or horizontal launch projectiles, keep in mind that we are forever going to be separating x and y coordinates. And what we do for x is different from y. So x only pertains to itself, y only pertains to itself as well. Okay, pig hanging from the ceiling. All right, again, we don't care about the objects, we don't discriminate, so it's just going to be another box, but it's hanging from a ceiling, so it's not magically hanging due to air resistance. So you should probably be thinking about what that force is, and that's essentially force tension. I didn't say how many ropes or whatever it's hanging from was there, so we're just going to depict one, and Ft is equal to Fg for us. Okay, an animal floating in a pool. So this is where water is involved. So the force is going to be a little bit different than what you're used to seeing, but we made mention of this earlier. Now it's again, the surface is technically the pool, so still making contact. However, it's no longer, because it's water, it's not Fn, it's F buoyancy. So Fb is equal to Fg in this case. So again, at the heart of it, pretty much everything looks almost the same. It just depends on, is something accelerating? If so, in which direction and by how much? So you're just basically depicting arrows to depict the accelerations. Pay attention to any mentions of keywords, whether it's at rest, falling versus free falling, constant velocity, and so on. Okay, are the balance forces balanced or unbalanced in the picture? Well, obviously, in a normal year, you guys would have access to these worksheets, and this is anything but a normal year. So let's see. Okay, so let's just look at this example. Is this one balanced? Well, yes. We have 5 newtons and 5 newtons on each side. Technically, on the left, you should put it as -5. In fact, you should all do that going forward. But this was a worksheet that I have control over. Now, in this scenario, let's look at if this is balanced. So we have 5 newtons to the right, 1 newton to the right as well. So that makes it a total of 6 newtons to the right. We have 2 vectors of 3 newtons each to the left. So the 2 3 newtons are technically -3s each. That's -6. And on the right-hand side, we have +6. So those are balanced in that scenario. Let's look at our vertical ones. We have 5 newtons upwards, and we have 1 newton and 4 newtons there. So each of them are 5. So 5 newtons and 5 newtons are there. So that one, this was considered to be balanced. Let's look at this one here. We have 4 newtons on the right, on the top, and 4 newtons on the left. Now, unfortunately, the one vector on the top is not relative to the one on the bottom. So even though the values say the same thing, the vector on the bottom is not the same size. So that would be considered wrong. So just pay attention to little things like that. Now, on the right-hand side, we got 5 newtons and 3 newtons. So it's a total of 8 newtons. And on the left-hand side, it's -10 newtons. So you've got -10 on the left and +8 on the right. So horizontally, this is definitely not balanced. So now here's my explanation for you. Like I said, that top arrow was a little bit longer than the 4 on the bottom. So we're going to go ahead and adjust the numbers. We can say that theoretically, based on the size, the vector on the top should have been 6 newtons. And in order to balance it out on the bottom, we're going to add a second vector to the bottom and put it as 2 newtons. So now we got 4 and 2 on the bottom, making a total of 6 downwards, or -6. and then you got +6 upwards. So those two are balanced vertically now. And for us to balance the one horizontally, remember we had -10 newtons to the left. So we used to have a total of 8 newtons to the right. So in order to balance it out, we have to add a third vector with a value of 2 newtons. And as you can see, it's smaller than my 3. So it's a total of 10 newtons to the right now. And now this vector force by diagram is balanced. Okay, now let's look at this example here. We've got 8 newtons to the left, -8, and we've got 8 newtons to the right, +8. So those are balanced. Now, the vertical ones, we've got 2 5 newtons on the bottom, so that's a total of -10 newtons, but only 5 newtons going up. So that's clearly not balanced. So for us to balance that, we need to add another second vector going up to our FBD, also make it 5 newtons and relatively practically the same size. So now it's balanced out. So going back to the original questions, key thing here, unbalanced forces cause objects to move. Essentially, they cause acceleration. Acceleration causes it to move. And then we're supposed to look at if the forces were balanced, which we did, and if they weren't, we're supposed to add additional forces, vectors to balance them out. Balancing means to get it to 0 newtons overall. Okay, so some basic stuff. We can tell how forces are balanced or unbalanced by looking at the arrow sizes and the numbers. If they're equal in size, either in horizontal or vertical direction, again, what happens on the x is strictly for the x. What happens on the y is strictly for the y. The net force is the sum of all forces acting in objects. So it's the result of all the forces. And when we refer to net force, again, we only refer to net force in directionals. So there's a difference in net force in the x direction versus the net force in the y direction. So when we get to problems later on with Newton's second law, we'll discuss that more in depth. And finally, if the net force is 0 newtons, the object is not accelerating. But the key thing is it could be moving. So just because something is balanced doesn't mean that it's stationary or stopped. You could be balanced and you could still be moving. Think of the skydiver reaching terminal velocity. Think of the car that is moving to the right and on a cruise control. So again, it's just that if the net force is 0, it just means that it's not accelerating. It doesn't indicate whether it's actually moving or not. It's a different ballgame. Okay, so that's pretty much it. Hopefully you enjoyed this, and hopefully this made a whole lot of sense. Just basically remember to always draw your FBDs and take the scenario at the moment. Don't think about the picture beforehand. Don't think about the picture afterhand. Just that specific moment. Yeah, hope you guys have a wonderful day.